Okay, this next lesson deals with a very similar topic to what we just dealt with in the last one, which is gas solubility. We're now looking at how gas is dissolved in water. The biggest difference here is gas is hardly dissolved at all. There is a slight, ever so slight van der Waals thing going on here to allow them, but most of them are non-polar and therefore not very soluble in water. But you know, in order for fish to live, the oxygen, which is very non-polar, has to bond with the water, but the bond is so weak that it comes apart real easy, so we have to be able to figure out ways to get the gases to dissolve. So that's what this lesson is going to be all about. And the fact that it is a very weak bond means it's going to fall apart very, very easily, and we don't want it to do that. We have certain temperatures that the water has to be when water is dumped into the river by a power plant. Because when it gets run through the power plant, it gets extremely hot. They dump it into the river, and it's so hot that the fish die in it. So there are regulations on that kind of thing. So these are the types of things we have to be concerned about. So what's the best way to look at this? Well, the best way to look at something like this is to identify with something that we commonly do. Now, many of you like soft drinks, and the most popular soft drink amongst those your age is Mountain Dew. So we're going to talk about Mountain Dew. We know Mountain Dew is a soft drink because they call it a soft drink because of the bubbles, makes it feel light. The bubbles are carbon dioxide gas, okay? So think about that bottle being taken out of the refrigerator on a warm day. You pour the Mountain Dew into a glass and observe what is happening, and what do you see? Well, like I said, you're going to see bubbles floating to the top. And those bubbles are carbon dioxide, which means it was dissolved in the solvent, which is water. Even though you got this kind of greenish yellow thing, whatever that is, that's not really the solvent, that's just a dye added to it. The solvent this thing is mainly water. So the question is, how did they get a non-polar gas to dissolve in polar water? And like I said, the best way of thinking about this is to make sure that you have a drink that stays bubbly. What are we going to do to make sure it doesn't go flat? Okay? So if you think about it on a hot day, you know that if you pour a glass of Mountain Dew and let it sit for a while, it's going to get flat. Flat meaning that the carbon dioxide leaves and is not there, and you take a drink of that and you just go, oh, this is just nasty. All right? So obviously this is going to involve temperature. We have a temperature change that rose, it went up, and somehow that has an effect upon the ability to stay bubbly. So the best thing to do is to make sure that you keep the temperature cool. Now, why is that? Well, again, it goes back to what we talked about in the previous lesson. It goes back to kinetic energy. When you decrease the temperature, the motion of the molecules decreases because the kinetic energy decreases. And therefore the collisions are not as hard. Anytime you have a collision like that, bubble's going to come off, which is why if you just look at the glass and you see all the bubbles streaming off of there, it's because it takes virtually nothing to break them apart. Just the presence of your hand on the glass is going to cause that to bubble up even more. So when you increase the temperature, it's going to increase the speed and they're going to collide, and your carbon dioxide is going to disappear and your solution is going to go flat. And this is why you go fishing, that when you go fishing on a hot day, it's generally not a good idea to go on a hot day, but sometimes, you know, you just want to get away from it all and just sit there. And so you put your line in the water and you want to figure out the best way to get a fish. Well, most rather veteran fishermen will tell you that you want to find a deep area, a deep part of the river or the lake or wherever it is you're at, and put your line in that area as deeply as you can, because the farther down you go away from the surface, there's less contact with the sun rays, and so it stays cooler at the bottom than it does at the top. That means that the water molecules are not moving very much down here where they are up here. Now, if it's a river, it also probably isn't going to be so much in contact with the current, because the current will drive off a lot of oxygen because it's constantly moving water, it's constantly colliding. But if you're in like a lake or something like that, find the deepest part of the lake on a hot day and just put it down there. Your chances are better of getting a fish than in some shallow surface. Okay? Another reason the Mountain Dew would be flat is because there's nothing forcing the gases to stay. If you pour the bottle of Mountain Dew into your glass and let it sit, and let's say the temperature, and you put it back in the fridge even. Now when you put it in the fridge, it's going to maintain its bubbliness somewhat, but the fact that you have it in an open container, there's nothing keeping the particles inside the solution when they break apart. All right, so what you want to do is find a way to apply a force to the top to keep that stuff from coming out. And that's what the bottle cap does. In fact, when you open up a bottle, a 2-liter bottle of this stuff, or you open up a can, what's the thing you hear? A hiss. The hiss is a rush of gases coming out all at once because they're going, yeah, free at last, oh my, where am I? Anyway, so when you allow a release of the pressure decreases, then these things rush out. Okay? So keep the pressure on. So that is why you always put the cap back on the bottle so whatever gases are remaining in the Mountain Dew stays in the Mountain Dew. Now, a third way, the best way to think of this is, what is the most fun thing to do with a 2-liter bottle of soda? Well, duh, shake it up. What happens when you shake it up? Well, what are you doing to the solution when you shake it up? You are forcing collisions, and collisions are not good for soda pop. In fact, if you do it really hard, you can feel that plastic just get really tight. If you open it too soon, you know you get this volcanic reaction like, well, all the liquids comes out all at once. But why are the liquids coming out when it's only the gases being released? Well, it's because all the gases are getting released, or very close to all the gases getting released all at once, and they all want to get out at the same time, and because you got those narrow openings there, it's going to keep it from getting out without shoving the water along with it. So like you got these bubbles down here, you got all this liquid around it, it just wants to come out, and the water can't get out of the way fast enough, so you get this explosion. Not a real explosion, but it seems like an explosion. And of course, if you like shake it up and give it to a friend of yours and kind of walk away, you're very well familiar with that. So all those gas molecules want out now. I want out now. So whatever's in the way is going with it. So the 3 ways to get a gas to dissolve in water or any liquid solvent, whatever you're dealing with, are decrease the temperature, increase the pressure, and do not agitate the mixture. Make sure it's a calm mixture. So, the solubility chart in water will likely be opposite to the chart with a solid solute. Why? Because the solubility chart for the solid, as the temperature increased, the curve went up. Because it allows dissolving to take place because of the collision between the water and the ionic crystal. Not the case for gases. Now, that chart that we were looking at for the last one, right here, we identified the 3 gases here. HCl is this curve right here. NH3 starts way up high and just drops dramatically as it gets close to 100 degrees. And then sulfur dioxide drops quickly and just kind of levels out and slowly decreases over there. Okay? So, the difference here too is because there's such a, well, we're going to have the same label, but the charts I'm used to seeing for this for gases is that they compare it to liters of water, which is 1,000 grams of water. But they've accounted for that with these values here. So The label is going to be exactly the same. I may have said it differently here, but let's find out here. Gotcha. Okay, so let's check this out here. I don't think so. I think we're good. Okay, so let's suppose we want to find out the solubility of HCl in water at 10 degrees Celsius. HCl 10 degrees Celsius. Okay, so let's check it out. So HCl is right here, right there. At 10 degrees Celsius, it's right there. And that looks like it could be maybe 23, 24, somewhere around there, grams of HCl dissolved in 100 grams of water. So the label will be then, what? I got 78. Whoa, I don't think that's right. So yeah, that's not, let's take another look at that. What did I do? Did I take the wrong temperature here? I got 10 degrees, and we're looking at HCl. I think I've made a mistake here. So let's go back to that. Oops. Over here. HCl. Oh, okay. I was looking at the wrong line. It's this one right here. So at 10 degrees is right there. So it's like just under 80, 377, 378 grams. What was I looking at? Oh, I'll bet you this line right here, and I saw the HCl arrow. It's tough getting old. So, 78 grams per 100 grams of water is how you would describe that. Okay? Your assignment, find the solubility of those gases at those temperatures using that chart that I have accompanied with this. Good luck.